Hello, everyone, and welcome to today's SONiC webinar on advancing AI infrastructure with SONiC, high-performance networking for scalable AI fabrics. I'm Sunny Tai, Marketing Manager at the Linux Foundation, and I'm excited to be your host for today. Before we get started, just a few quick housekeeping notes. This webinar is streamed live on LinkedIn and is also being recorded. We'll be able to catch the full recording on SONiC YouTube channel after the event. If you have any questions for our speakers during the webinar, feel free to drop them in the comment section on LinkedIn at any time. We've set aside the last 15 to 20 minutes for Q&A, and we'll do our best to get to as many questions as we can. So as a reminder, this is an official Linux Foundation webinar, and all participants are expected to follow our code of conduct. Please keep the discussion respectful and constructive throughout the session. So now onto the exciting part. We have an incredible lineup of experts with us today. Let me first introduce our moderator, Yanzhao Zhang, Principal PM Manager at Microsoft. Yanzhao brings deep expertise in data center networking and has been an active community member and contributor to the SONiC community. And joining Yanzhao today are two key voices from the SONiC community. Senthil Kumar Ganesan, SONiC Technical Steering Committee member and distinguished engineer at Dell Technologies. Senthil has been instrumental in shaping SONiC's architecture to support modern infrastructure needs. And we're also joined by Saurabh Kapoor, governing board member of the SONiC Foundation and director of product management and strategy at Dell Technologies. Saurabh plays a strategic role in guiding SONiC's roadmap and enterprise adoption. So together, we'll walk us through how SONiC is evolving to support the unique demands of AI workloads, with insights on features such as 800G connectivity, Rocky V2, dynamic load balancing, and more. So with that, I'll hand it over to Yanzhao to kick off the conversation.
Okay, thank you, Sunny. Good morning, good evening, everyone. So welcome this SONiC. So as Sunny mentioned, this session will highlight how SONiC is driving the scalable AI fabric, which is a hot topic in these areas, and also especially in this year. And we will touch base with how SONiC enable the 800G connectivity, and also the Rocky V2, dynamic load balancing, etc., some new AI features enabled in SONiC, and also enhancements for the existing features for AI workload. So we will explore the best practice and the real-world architecture, the deployment from the organizations, and also the who leveraging the SONiC for the high-performance AI networking, especially on the backend side. So thank you for being here. With that, I will hand over this to Saurabh to start the presentation. So Saurabh, please go ahead.
Thank you, Yanzhao. Hello, everybody. Great to be here. Thank you for joining. The first webinar session. We're very excited to kick off this initiative across the board. Before we get into the discussion today, let's start with a quick view into this. Picture yourself as a data scientist, right? You're leading a healthcare enterprise. You're tasked with a mission that could change lives. You're training a generative AI model that could revolutionize diagnostics, detecting disease faster and more accurately than ever before. Now, what you've done is you've assembled a massive cluster of about 8,000 GPUs. You've connected, billions of data points to it, and you've created a computational beast that is ready to tackle this challenge. Now, the stakes are high. Every second counts because your breakthrough could save lives. What you do is you hit run, expecting magic to happen, but instead you're met with a silence. Your GPUs are sitting idle hour after hour, sometimes days, as the network chokes under the weight of the AI demands. The massive elephant data flows, those torrents of data surging between GPUs, the bursty traffic patterns overwhelming the fabric, are stalling your progress. Networking is such a critical enablement in that, it's the information highway that allows these massive compute devices to talk to each other, enable that AI optimized, infrastructure. Studies show that 57% of your workload time is spent in networking, costing millions in lost productivity in dealing life-saving insights if you don't have your networking set right. And this isn't a hypothetical situation. This is the reality of the world we operate in today. AI is it's in a fast evolution here. As the explosion of compute capacity for AI traffic, is shaping up, the demands on the networking, are going to increase every day. And that's why we are here today. SONiC, an open source network operating system, is rewriting the rules of AI networking. It's powering the largest hyperscalers and enterprises today. SONiC delivers the scale, the speed, and the reliability to tame those elephant flows and handle bursty traffic to ensure that AI breakthroughs don't get stuck in the network. In today's session, we'll dive into AI networking, its unique characteristics. We'll talk about challenges of supporting massive compute demands, the cutting-edge features SONiC brings to champion this infrastructure, and we'll explore how to move quickly and drive that business transformation. So with that, let's get started. Right? In terms of the world of AI evolution, right? We're talking about uncovering patterns, detecting frauds, predicting weather or classifying images. It was powerful but limited, right? Working with thousands to millions data points to deliver those insights. That was your traditional AI, a foundation that changed industries. But now we're in an era of generative AI, and it's just about not understanding just the data, it's about creating it. Imagine AI that writes reports, designs graphics, or generates videos, synthesizing billions of data points into intelligence that transforms how we work today. These large models aren't just tools, they are engines of innovation driving business transformation at a scale we've never seen before. And with great power comes great responsibility. So, to harness this potential, organizations must move quickly to leverage AI to unlock that productivity and stay ahead. The catch here is that networks must evolve too, right? SONiC is that key to evolution that enables you to run AI promise into reality. So let's see how AI workloads are reshaping those demands. Right? When we step into the world of AI workloads, right, where the stakes are high, the network is an unsung hero. You imagine, these AI factories, the hyperscaler training, a foundation model with billions of parameters. It's a Herculean task, right? Consuming massive data sets over days or weeks with thousands of GPUs working in unison. These workloads, these are, bursty traffic, elephant flows, the network delays can stall the entire operation, costing millions in wasted effort and time. The fabric, must be a masterpiece where you have optimized topologies, robust load balancing to keep these GPUs humming at peak performance. When we shift to the fine tuning, a global enterprise which is refining a model for a certain application like a fraud detection, these are often on premise to protect that sensitive data. These are relatively smaller clusters, right? We're talking about dozens to a few hundreds of GPUs, but security is paramount here. And finally, inferencing, right? The heartbeat of an AI in enterprise, right? Picture a retailer that is using AI to recommend products in real time on premise in a conversational flow. The scale is smaller, sometimes a single host, but the demand for low latency, responsive fabrics is non-negotiable. From AI factories to distributed enterprise inferencing, SONiC delivers that flexibility and scale to power every stage of AI journey. But what makes AI networking so unique? Let's find out. So, let's address the elephant in the room, right? AI networking isn't just different; it's a battleground. Imagine GPUs talking to each other, exchanging massive data sets in milliseconds, right? You're talking about GPU to GPU communication. You're driving bandwidth demands through the roof. The traffic is bursty. Links are getting saturated in microseconds. You're pushing the fabrics to their breaking point. Your training jobs run for days, weeks. Every second counts here. And tail latency, it's a silent killer. Like a few slow packets can grind an entire cluster to a halt. And Meta's research, that was shared at OCP, paints it's a stock picture, right? Across the four models, they showed that 35% to 57% of an AI workload time is spent waiting on the network. From ranking tasks needing high injection, bisection bandwidth, that's millions in wasted GPU cycles, stalling innovation, draining budgets. So this isn't just a technical challenge; it's a business crisis, and AI networking demands the fabrics that help eliminate latency, maximum throughput, deliver lossless performance capabilities, and all of that is baking into SONiC, and it's not just getting ready for this challenge. It's built for it, and let's explore how. So when you look at the capabilities and optimizations that are needed in the network, right? And how does SONiC kind of turn this crisis into opportunity? It starts with building these AI fabrics that perform with precision, right? Let's look at the load balancing first. Imagine, traffic flowing like a symphony, perfectly distributed to keep these GPUs humming. You're talking about technologies like packet spray and cell spray across different, silicon vendor capabilities that scatter data evenly across the network. And then, capabilities like enhanced hashing using in-band transport fields like ECMP, ensuring multipath efficiency. Adaptive routing capabilities that helps take it further, dynamically adjusting paths based on the link quality, slashing latency without touching those control points, right? Let's look at the congestion control, right? The backbone of a lossless performance, right? DCQCN using explicit congestion notification to manage those per flow congestion, ensuring rocky workloads run without a hitch. The congestion control algorithms help fine tune those flows with probe-based precision. Technologies and capabilities like reactive, path rebalancing and fast link failover allow you to steer that traffic around failures in real time, optimizing your fabric. So, in summary, AI isn't just evolving; it's rewriting the rules of business. See a spectrum of technologies from AI factories to large enterprises. We're talking about billions of data parameters that are going into these models. We understand that networking is so critical, where you have significant amount of time a packet spends within the network. The power of all of those capabilities coming into the network operating system is significant. So with that, I'm going to pass it on to Senthil to help deep dive into the topologies and the architectures and some of the capabilities I mentioned here. Senthil?
Yeah, thank you, Saurabh. I'd like to take a moment to step back and clarify the various network fabrics involved in the AI, as there seems to be some confusion surrounding them. Later in the presentation, I'll delve into the design and requirements of these fabrics. For now, I want to introduce two new types of fabrics that recently introduced by the AI workloads. One is the scale-out fabric. The other is the scale-up fabric. Let's take a closer look at the GPU fabrics, right? How they are structured across different configuration GPU servers. And GPU servers can have a varying I/O interconnect based on their architecture and use cases. So in this illustration, I have highlighted one of the most widely used systems, NVIDIA HGX platform. This system includes 8 GPUs that are interconnected internally through a high bandwidth scale-up network, typically using an NVLink or NVSwitch in case of NVIDIA. This internal fabric allows for fast communication between this inside the single server. To enable communication across different HGX boxes across servers, this uses a set of 8 PCI interfaces per node. This NICs connect to an external scale-out fabric, what you see here in the beige color, allowing the GPUs to work in a concert across multiple nodes. Right, in the recent NVL72, the rack scale systems, the topology becomes even more integrated. Here, the scale-up fabric not only connects the GPUs within the nodes, they also connect across the nodes as well, spans across the nodes, effectively blurring the lines between the local and distributed GPU resources. Let's closely look at the scale-up fabric. Scale-up fabric plays a crucial role in enabling multiple GPUs to function as a unified system, sharing both compute and memory resources efficiently. It is often referred to as a memory fabric because it supports direct memory load and store and atomic operations between those GPUs. To achieve this level of tight integration, the scale-up fabric uses high bandwidth, ultra-low latency interconnects and switches. Compared to scale-out fabric, scale-up interfaces offering significantly higher bandwidth, making them ideal for intra and inter-GPU memory sharing. When it comes to scale-up fabric, today, mostly it's proprietary technology from NVIDIA. NVIDIA uses NVLink and NVSwitch. AMD uses Infinity Fabric, and Intel is using Ethernet-based interconnects. Open standards like UA-Link and UEZs are being developed to enable vendor-agnostic solutions. There is also a growing interest in the Ethernet-based scale-up fabric, with SONiC likely to be the network OS of choice. Right? This is just getting started. To be effective, the scale-up network needs a low latency, lossless communication and high throughput for small packets and minimal protocol overhead. All these are critical for enabling fast memory level operations between the GPUs. Like scale-up fabric, GPU scale-out fabrics extends the connectivity across multiple nodes, enabling efficient coordination and resource sharing at a much larger scale. This allows multiple GPUs across different servers to work seamlessly on a complex distributed workloads, such as AI model training, fine-tuning, or a large-scale inference. Scale-out fabrics are essential for building high-performance GPU clusters where the GPUs needs to communicate quickly and reliably over a network. Today, this is typically achieved using InfiniBand, high-performance Ethernet, or even custom-design interconnects. You might also hear these networks referred to as east-west fabric, a compute backend fabric, or a compute acceleration fabric, or simply AI fabrics. The standard term actually is scale-out fabric, so that to avoid any confusions. SONiC plays a critical role in this fabric. Its primary focus is to serve as a network operating system for scale-out GPU fabrics, offering flexibility, programmability, and scalability needed for this AI environments. Let's explore some of the common network fabric architecture used in the scale-out GPU system. We will focus some of the widely used systems. I have not covered all the designs here. We'll focus on some of the widely used designs. So let's look at the single-tier fabric design, right? This is a simple and effective starting for most of the enterprises to start with, right? It can support up to 1,000 GPUs, right? It covers most of it's ideal for a fine-tuning or inferencing workload with minimal network complexity, no need for advanced load balancing or congestion control. It's just single tier, so it's much more easier to control. So you don't have any of the complexities which we talked about earlier in the single tier design. So it is an effectively good starting point for a smaller enterprises. And the second one is the standard class fabric. The class topology is also used common in environments where the GPU servers lack an internal scale-up network, right? So basically, when a server, you choose a design based on the server architecture. If the server architecture is kind of not using an internal scale-up design, are not optimized for rail communication patterns, this is where you use the class kind of topology, which is much more powerful in terms of TCO with respect to the cable connectivity and other stuff, right? The class network also incurs higher latency compared to rail optimized fabric when you cross across node, because now even for if you want to go cross between multiple nodes, you have to cross another layer which increases latency. The next one we're going to talk about is a rail optimized design. This is the standard best practice for any large scale AI training using rail aware architecture. This reduces latency by minimizing the traffic going through signs. So most of the traffics are all localized. So the latency is reduced, and it avoids multipathing and congestion issues within that SUs, right? The scalable unit. So within this SU, you're still like initial single tier design, you're still within the first layer. So you don't have this kind of multipathing and congestion issues between those nodes. Only when you cross across nodes. And the algorithms which are designed today, the collective communication library algorithms are all mainly optimized for this rail paths. So they don't typically cross to the spine unless there is a failure, or some of the algorithms are you're running an even node, odd node. Sometimes it goes across the nodes based on the algorithms being used. So this works in hand with the CCL libraries and network level optimization. So this is the go-to network design for your scale out fabric. Pure or spineless rail is a variant of the rail optimized design. In this case, there are no spines because most of the traffic anyway it's routed to, and if there is a failure, so it can route internally via the scale-up network, the traffic. So if you're sure about your workload that all your algorithms we are using is all on rail optimized algorithms, so you can use it, saving much more cost with respect to the topology. Again, this can scale up to 1K GPUs. With the multi-plane designs, it can go up to 2K in a single tier. So what you're seeing in the fifth is the multi-plane fabric designs. These are the next-gen disaggregated fabrics made up of multiple independent planes. A single NIC has been split across multiple planes, and connected to a different set of pure rails. So think about it. Typically, right now, they're talking about 2 planes, or it can go up to 8 planes. If you have earlier listened to Microsoft talking to OCP, so they're talking about skinny links where 8 into 100 links. The 800 link is divided into 8 cross 100 links, and you can have such different planes of connectivity. This improves false elements and scalability, and also it also covers multiple servers in a single tier, right? So now we can go up to 2K or 8K in a single tier itself. So that way you can still keep the traffic localized. There's no load balancing or congestion kind of thing, right? You can mitigate all those things using this design. And this design requires a NIC support to fully support this model, unlocking greater flexibility and performance. The last one I want to talk about is the Converged GPU and storage fabric. This design, we started seeing this kind of designs evolving in the field based on the distributed inferencing and the GPU direct storage of the CPU async, right? So whenever right now the distributed inferencing is the big talk of the town, where you have distributed KV caches. In order to perform an inference, you need the storage connectivity, the KV caches, which is stored in the storage distributedly. So it has to be brought back for the GPU for the compute to process and inference your request. So this kind of designs are becoming more popular as well, where storage is connected directly to the scale out network. Right, these are the physical designs I would like to we covered today. What are the logical thing needed for this design? So typically for an AI fabric, the logical design is very simple. It starts with layer 2, layer 3 topology with BGP. Unless you're looking for a multi-tenant fabric, a layer 2, layer 3 would do for most of the AI fabrics, with Rocky V2 and the DCGCN for congestion control for a lossless fabric. Right, if you're going for multiple tier of switches, then adaptive routing and switching becomes mandatory, because you need to have the even load balancing so that you're not creating congestion and full flow collisions, which are essential for job completion time. And hardware link failovers, support the features for hardware link failover or bidirectional BFD forwarding is needed to mitigate the link failures quickly, right? So as far as the network features are concerned, it's a little bit simpler compared to a traditional data center. And if you're going for a GPU as a service customer or something like that, you want to provide a multi-tenant environment, then depends on the number of tenants, either you can go with the VRF or a L3 VXLAN based solutions. Right. Coming back here, right? So we have seen what are the two new networks which has been defined, and what kind of designs we need and what kind of feature set we need, right? As Saurabh talked about earlier, a significant portion of the time in distributed AI workload is spent on communication between the GPUs, not just computation. Several key factors contribute to the communication delays: transient oversubscription of the links, flow collision and link failures, and incast scenarios where multiple senders overwhelm the single server, right? To address this challenge, SONiC has been optimized specifically for AI fabrics, enabling high-performance networking for GPU servers. It supports ultra-high radix switches with large number of high-speed ports, such as 400, 800 gigs, which allows for a flatter, more efficient network topologies and easier congestion control. The de facto standard for RDMA over Ethernet, enabling direct memory access between the GPUs. This reduces latency and enables lossless communication, preventing timeouts and retransmission, which is essential for the job completion time for the AI workloads. SONiC also supports adaptive routing and switching with enhanced hashing mechanisms to minimize collision and oversubscription. Features like spray mode, which we talked about earlier, are supported in SONiC, right? So this has two modes, whether you're flowless switching or a spray mode. The spray mode requires an out-of-order placement support from the NIC in order to evenly process and reorder the packets which are sprayed by the switch. Finally, in any large GPU cluster, link failures are inevitable. Traditionally, these failures are reported back to software, which triggers a routing protocol update and recomputes the forwarding state and then reprograms it. But SONiC aims to reduce this impact by enabling faster, software-independent failure detections, ensuring minimal disruption, and help maintaining training job completion times. Right? Managing the complex AI infrastructure requires a robust tools for visibility and control. SONiC provides a unified management framework that supports REST, GNMI, CLI, and Ansible through SONiC data models, and it has efficient congestion and data packet monitoring observability counters for you, so that and histograms where you can pull those data for troubleshooting, and a streaming telemetry offering real insights to the network. The SONiC provides an optimized NAS as for the AI fabrics. Right. So when I initially presented during OCP, right, so this kind of designs were not there, and then a lot more changes are happening, right? So there are quite a bit of changes happening in the AI fabrics as we speak. Within few months, right, we go through this lot of changes based on the models and everything. And let's look at what's new and what's next with respect to AI networking, right? As AI workloads evolve, so does the underlying fabric that supports them, right? Here are the key trends and innovations shaping the future of AI network fabrics. Modern NICs and DPUs are becoming smarter, taking on more responsibilities traditionally handled by the network fabric. Capabilities such as entropy generation, multiplane support, and packet spraying and reordering are increasingly being handled by the endpoints. This shift could significantly simplify the core networks and reduce congestion and improve performance, right? So basically, the majority of the heavyweight features are taken by the endpoints today, right? And emerging optical technologies like linear pluggable optics or co-packaged optics, these are expected to become the norm of the future of data center due to their power efficiency and better signal integrity. To support this hardware transition, SONiC will need to evolve in its platform layer to accommodate this new transceiver architecture and operational models. There are new traffic patterns which are coming up with the growing user parallelism and large-scale model architecture introduces new, more complex flow characteristics. Initially, we were talking about elephant flows, bursty traffic, but if you see the recent introduction of the mixture of expert models, training introduces data-dependent and irregular communication patterns that demand fine-grained control at the network level. Now, previously it used to be elephant flows, and now it is slowly changing based on the model evolution, right? So now in the expert parallelism, they're activating only the experts needed, and the communication library which is used for that transfers much less data compared to, but it needs a frequent transfers, and latency becomes more critical in those cases for inferencing. Right, the inferencing was typically used to done in single node, but with the distributed inferencing is no longer in a single node task. With the distributed inference, where different expert layers of the model are spread across multiple nodes, latency becomes critical. The fabric must be optimized to handle large volumes of small latency sensitive messages, ensuring fast and efficient inference pipeline. So previously, the tail latency used to be the key, but now latency is becoming more key for the distributed inferencing kind of pieces, right? So the initial requirements we were talking about is quickly changing with respect to AI fabrics, and SONiC needs to adapt to all those stages. New standards such as UEC and UA-Link and concept like in-network compute are beginning to define the future of AI fabric, and SONiC must be ready to integrate and support these innovations, ensuring compatibility with the next-gen AI infrastructures. To scale seamlessly and efficiently across thousands of GPUs, a robust high-performance network is essential. The right network can truly make or break your AI cluster performance. The industry is now heavily investing in Ethernet as a foundation for next-generation AI infrastructure, offering performance, scalability, and cost effectiveness needed for the Gen AI workloads. Ethernet is also beginning to gain traction in the scale-up GPU fabrics, further extending its role beyond scale-out use cases. SONiC is ready for AI. It's already been widely deployed in cloud enterprises and neo clouds for the next generative AI environments for scale-out fabrics. SONiC is also making inroads in the scale-up fabrics, as we talked earlier. To align with these advancements, we are restarting the SONiC AI work group, focused on prioritizing features that matters most for the AI infrastructure. Right? We invite you to join the SONiC community and be part of this exciting AI networking journey. Thank you.
Awesome. Thank you, Cynthia, Mr. Rob. And Yajao, I think we can get started with the Q&A.
Sure, yeah. Thank you, guys. Can you hear me okay? Sorry for my, I had some microphone issues just now. So, okay. So please feel free to drop your questions to the chat window. So we will try to answer those questions. So I would like to begin the Q&A sessions by directing the faster question to Senso. So here's my question. So how do recent enhancements in SONiC like the 800 gig connectivity and Rockway 2 translating to the real world performance gain for the AI workload.
So as we just talked about, right, the high performance AI workloads are foundation of model training, right? The mixture of expert distributed inference generate massive east-west traffic between those GPUs, right? The increased bandwidth per node with 800 gig links can handle more far more, reducing the risk of network bottlenecks during collective operation. Example, all reduce or all-to-all traffic, right? The flatter topologies, right? 800 gig enables higher radix switches, which reduces the number of hops in the network. Fewer hops equal to lower latency and easier congestion control, right? And with the proper DCQCN and Rocky V2s, we enable delivery without retransmissions, right? Which is essential for synchronous networking. So with the retransmission, again, you're causing delays on the job completion, right? With this kind of features, that is how we optimize SONiC for this AI workloads today.
Thank you. So the second question is, what are some key considerations or challenges organizations should be aware when they designing the AI networking fabrics with SONiC? I guess that question is to Sarab.
Okay. So when we look at some of the key considerations, right? Designing AI network with SONiC, the three important elements that we need to be careful of, right? One is the feature functionality, right? We spoke about tail latency as an important consideration, right? Congestion management, load balancing, and adaptive routing capabilities, right? So these AI workloads are sensitive to latency, and a few slow packets can create a bottleneck in the entire system. So it's very important to consider how do we build these fabrics, what feature functionality, what do we use for congestion management, what do we want to use for adaptive routing, making sure the fabrics are fine-tuned to the kind of workloads and the scale we're looking at. When we talk about scale, right, Senthil mentioned different topologies we have, the real optimized architectures. These AI fabrics, you need to scale to thousands of GPUs and without performance degradation, right? And with non-blocking designs, ensuring that these fabrics are set up, to champion their environment. We're talking about high radix switching available now with good port density. You're able to set up these fabrics and go about it. The third important consideration that was often overlooked in the previous world with traditional data centers is fabric automation in AI ops. Right? That is one element that is becoming increasingly important because we're talking about infrastructures that are running at peak capacities most of the time, right? You're talking about a consumption model which is GPU per second. So you're seeing AI factories and enterprises that are running these infrastructures at peak capacity to take advantage of the investments. So your traditional way of SNMPs and syslogs and fabric setup is not going to work anymore. You need cutting edge tools and technologies that help you simplify that lifecycle management aspects. Ease of fabric deployment, capabilities that help you move faster. You need technology and capabilities that help you, go on the AI ops side, quickly. There are, capabilities that are coming, around, self-remediation, auto-healing fabrics that are, taking advantage of the streaming telemetry available in SONiC to get real-time insights and take predictive actions based off it. And now you can, have the human interact with it, or have certain actions that can, the machines can take, automatically based on, the historical patterns, right? So I think the third element on AI ops and automation is going to be another important consideration when we look at these AI fabrics.
Thank you. So I got a question from the online. So the question is, how mature are the collective library for multiple AI accelerators generation to support the networking topology?
Yeah, I can take that
Thank you.
answer, right? So the collective libraries are ongoing development, right? It has been pretty mature. It has been there for quite some time, and it's open sourced environment, right? For NVIDIA, it's Nickel, and AMD, it's Rickle. Those are the prominent collective libraries, and for Intel, it's HCCL. So all supports most of the algorithms, and as you see, every release, every 3 months, I see a new algorithms getting introduced or new optimizations getting introduced in Nickel, right? It's a significant advancement and ongoing development. And the industry-leading companies are developing their own collective communication libraries. Like if you have seen Microsoft has MSCCL, and Meta has their own enhancement for CCL, and all those contributions are coming back to the CCL community. I think Microsoft's CCL is already merged with RICL, right? So those changes are also coming in. There are significant ongoing development, and then wherever they want to take the performance out of it, right? They're optimizing that for that nickel, right? So based on the algorithms, and there are a lot of parameters when you come to nickel and RICL, which you can tune per the server so that you can get optimal performance out of your AI clusters.
Thank you. Okay, we have another question. So we have seen growing adoption for SONiC in both the cloud and enterprise AI environment. So can you share a use case or customer story that highlights the SONiC impact in this space?
Sure. I can take this one. And this is a very recent one, with a user called Hotile, right? It's a company that is transforming AI accessibility for enterprise play. And Hotile is leveraging SONiC to build that reliable, efficient AI cloud solution for different workloads they're running. And by deploying SONiC, they reported, some of the really cool advantages they've got. They've created a multi-vendor stack. They're able to support these high performance, computing needs. They're able to host, different applications for the end, users with machine learning to big data analytics. These are, low latency fabrics that they have, with microsecond level, data transfers. They run workloads from training to inferencing, and have gone about, taking advantage of that. So very cool to see all their action, and there's a public case study on how they've gone about this journey, with SONiC. The second one is, what we can share from a Dell perspective, right? Dell IT is a great example, and it's also on the mantra of, practice what you preach. So Dell IT has taken the journey with SONiC. We've got about 2,000 plus switches that are in production across a variety of workloads. We're on a path for 10,000 switches by end of this year. And this spans from 23 global data centers to remote offices, branch locations, with all the distributed inferencing that is happening on the edge, and variety of workloads, right, from your traditional enterprise applications to AI infrastructures, right, infrastructures that the engineering teams are using to build these AI technologies, and services teams that are hosting different chatbots that are interacting with the users based on the on-prem local database to interact with, right? So variety of workloads hosted on-prem across different infrastructures, all powered by SONiC with these optimizations we discussed today. So it's very encouraging to see SONiC being there, Ethernet delivering capabilities that are needed for these modern infrastructure, delivering choice of GPU, choice of NIC connectivity from an infrastructure perspective, and then optimized for different topologies and architectures. So those are a couple of examples, on top of the head.
Thank you, sir. So let's see if any more questions. Okay, I do not see any more questions. So with that, I will hand over this back to Sunny.
Awesome. Thank you, Anjao. So thank you so much, everyone, for joining us today. A special thank you to our speakers, Cynthia and Saurabh, for sharing their invaluable insights, and to our moderator, Yanzhao, for guiding a great discussion. So if you'd like to get more involved with SONiC, we encourage you to join the SONiC Foundation, become a part of the community, helping to shape the future of open networking. Whether you're contributing code, exploring use cases, or looking to collaborate, there's a place for you. And if you're interested in attending future SONiC events or any of our community meetings, you can head over to the SONiC website or visit our events page at sonicfoundation.dev/events for all the latest updates. And again, the recording of today's webinar will be available on SONiC Foundation YouTube channel. We also have more exciting webinars coming up, so be sure to follow the SONiC LinkedIn page to stay in the loop. Thanks again, and we hope to see you at a future SONiC event.
Thank you.
Thank you, everybody.